let's continue. So today the topic is F statistics. It's actually the last of these kind of general topics before we go into more or less concrete examples of the GLM, to which you then can apply your whole tool set of computing estimators and TNF statistics. The way I will introduce F statistics is, I assume, quite different from what you heard about F statistics before, because I assume that you heard about F tests in ANOVA, and we, depending on how much time we have, we might come back to that actually, but we'll see. Today I'm introducing F statistics from a different perspective, which is, and of course, also the more interesting perspective, in my opinion, namely from the perspective of model comparison. And the basic idea behind that is the notion of likelihood ratio tests. So we start with the idea of a likelihood ratio test. And then, basically tailor this model comparison criterion to a specific model, which is of course the GLM, and a specific framework within the GLM to introduce the F statistic itself. And then we are going to look relatively briefly into the distribution theory of F values. Again, with this bipartitioning of looking at the F statistic as a number itself, which might be interesting, like for the t-value, and then using it in hypothesis testing based on its distribution, which one may or may not want to do. And finally, maybe look at a simulation that is just a visualization of what I will have covered until then, essentially. Okay, so the first thing to talk about are likelihood ratio tests, and this is fairly interesting and important for general cognitive neuroscience and science in general, because I assume that in a couple of your sessions on cognitive neuroscience, you came across the idea that people want to do model comparison. So people like computational modeling. Some people do a lot of it, and if they do computational modeling, they are always then or what they have to do, and what is an inherent part of this computational modeling approach in cognitive neuroscience is to do model comparison to see which model is better. So have you come across that in Ulf's classes? Did you talk about model comparison for reinforcement learning models, or for what kind of models? Okay. Does anyone remember what kind of models? Some models, okay. Anyway, at least you talked about model comparison. So in general in cognitive neuroscience, when people say models, they always think of Rescorla-Wagner. So this thing where you have something like some value function. They usually omit indices because that's too much equation stuff for cognitive neuroscientists. Now dissing everyone this morning. And then they have these Rescorla-Wagner reinforcement learning models, and then they need to do model comparison, and then they use things like BIC and ARIC and so on. That's all great. There is also, in terms of Bayesian inference, model comparison is also a big topic. So model comparison is something that is important if you use a modeling approach. Now, model comparison essentially refers, of course, to the comparison of two quantitative theories for some data. So that's essentially what it means. So it comes down to comparing two quantitative theories to explain some data. And of course, this is really at the heart of science. So you have some data, and now you have different ideas about how this data is generated outside in the world, and you want to compare different theories, and the smallest set of theories that you might have to explain some data is that you have two theories. If you only have one theory, that's of course not a lot. So if you think about that, people like the free energy principle, that's great, but it's somehow only one theory at this point. So there's not really a competitor. So it helps to have two theories if you want to adjudicate between them or compare them. And so the most basic thing that you can do is to compare two models. In explaining some data. So a very basic procedure, basic but also important procedure in terms of probabilistic models. So if you deal with models that actually make probabilistic predictions, unlike things that are also very popular these days, like deep learning approaches that don't make probabilistic predictions, only if you actually put them into something, then they get interesting on their own. They are not that interesting. If you have two probabilistic models, then you can compare them based on what is known as a likelihood ratio test. So what does that mean? So the first thing is that you need some data. And of course, because we will talk about the GLM, our data, you can see this right, is again a vector of n dimensions. It's just like 10 data points, for example, or 1,000 data points. And this is something that you observed. So you have these data, and now you have two theories about how these data came about. And because you followed the approach taught in this course, you have probabilistic models, which we will call P, maybe M1, and another model P M2. So these are probability distributions over the data. And then the idea of a likelihood ratio test is that you evaluate the probability of the observed data under model 1 and compare that to the probability of the observed data under model 2. And the way you compare that is by forming a ratio. Yeah, so very intuitively now, if the probability of the data that you actually observed under model 1 is, let's say, 0.7. So now not talking about probability densities here necessarily, but really about probabilities in the discrete case. And the probability of observing the data under model 2 is smaller, so let's say 0.1, then this ratio will give a large value. If you have a reverse case where the probability of the data under model 1 is low and the probability under model 2 is high, then you will get a low value, just by means of this ratio. So you have to divide 0.7 by 0.1 and get 7, and here you have to divide 0.2 by 0.8, so you get something like 0.01 something. So that's a fairly So basically this likelihood ratio, so let's call this likelihood ratio, criterion gives you a number that if it's large, it says that your data is more likely under model 1. If it's small, it says that your data is more likely under model 2. Then you can, of course, come up with some threshold criterion where you say, okay, now I believe that, and this is what people fight about all the times, or not fight about, but discuss all the times, but it's kind of a wasted discussion because it's a continuous measure, and you just have to deal with it, that you get some value out of it. So that looks fairly simple, I assume, but the devil is then sometimes in the detail. So first of all, what is meant by the probability of the model of the data under the model? So these probabilities, they refer to the probabilities or the probability densities that you get after estimating your parameters. Yeah, so you know that we have some parameters in the GLM, for example, and that we can estimate them. And if we want to apply this criterion, we first have to estimate the parameters. So you might put a little bit here that if you have a parameter vector that this has already been estimated, for example, using maximum likelihood. Yeah. So these probabilities of data under a model are always under the assumption that the probability for each model itself has already been maximized, so that you're trying to get the highest value of the probability of the data under a model before you actually compare them. Yeah. So to now link this logic of model comparison to the GLM and actually apply this model comparison idea of a likelihood ratio, maybe I should not call it test at this point, but just likelihood ratio. The first thing that one needs to do is to actually log transform it. So instead of looking at likelihood ratios, what we will be interested in, if we apply this model comparison criterion to the GLM, a specific part of the GLM, we are actually interested in log likelihood differences. And this is fairly straightforward. So if we have our likelihood ratio, so let's again call that P1 divided by P2. If we now apply the logarithm to the whole thing, we get, of course, the log of this minus the log of this. Yeah. So that is then a log likelihood difference criterion. Is just, that was just a log transform, nothing has happened. The idea is still that you compare two models by means of the ratio of the probability or probability density of the data under each model. Yeah. So now the question is, how do we link this to the GLM, and what kind of models do we actually want to compare if we're looking at F-tests? And the basic idea here is to look at what is known as nested GLMs, or you can also call them partitioned GLMs. Let me find where I'm in. Yeah. So now we're trying to give some meaning to actually these PM1, PM2 that we're comparing here. Yeah. So what are those? Now, think again of the GLM, where yeah, you know how the GLM looks by now. Where X is an n times p dimensional design matrix, and of course the design matrix embeds together with the beta parameters your model, right? So we looked at different things previously, like simple linear regression and univariate Gaussian. So depending on the form of the design matrix and the beta parameters, you have a different model. And we are now interested in basically a model partitioning of such a model. So we assume that actually P is larger or equal to 2, not 1. Otherwise there's nothing to partition. So the design matrix has at least 2 columns. Normally it has more. So that we can write the design matrix as follows. X1 and X2, where now X1 is an n-dimensional times P1 matrix, so it has P1 columns, and X2 is an n times P2 dimensional matrix, so it has P2 columns, and P1 plus P2 equals P. Yeah, and I guess one might want to have further restrictions so that P1 is at least 1, but we don't want to over formalize things, or at least I don't want to do that. So just think of the design matrix being split into one set of regressors and another set of regressors. Yeah? So for example, if you think of simple linear regression, where the design matrix looks like this, as you all know, then of course it's very natural to split the design matrix here and have then X1 being just a column of ones and X2 being the values of the independent variable. And yeah, we don't want to over formalize things in the way that X1 needs to be a matrix. It doesn't need to have, so if you split it somewhere else, this matrix, then you don't get anything, don't have anything left. Yeah. So we're splitting the design matrix, and correspondingly we are splitting the beta parameters. So now getting rid of that and returning to the case above is that we here split our beta parameters into the beta parameters that belong to the submatrix X1 and the beta parameters that belong to the submatrix X2. So this is p-dimensional, and beta 1 is now p1 dimensional vector, and beta 2 is a p2 dimensional vector. Yeah. So the data we don't have to split, and there's no, so the data remains the same, and the error remains the same. We're just partitioning one, if you want, big or full design matrix into 2. And by this procedure, we actually, you can also view that as defining 2 models out of one original model. Let's call now one the full model. So the full model is just y x1, x2, beta 1, beta 2, plus epsilon, and a reduced model is using just x1, just the beta parameters that belong to a design matrix x1, and everything else remains the same. Yeah. So these are two terms that will come up now repeatedly. So the full model and the reduced model. And with F statistics, you're always comparing a full model, which has all the regressors, to a reduced model, which has just the first regressors. So now you can say, oh, can we do it differently? Yes, you can do things different, but currently so what we are concerned with today is F statistics, and in the F statistics is a scenario for likelihood ratio-based comparisons. One always compares a full model to a reduced model, and this is where this notion of nested model comes in. So nested, so the reduced model is obviously part of the full model, so it's nested in that. Yeah.
How do you know where to split the model?
That's your scientific creativity. So the So you want to compare two models, and then you need to, of course, always know what the columns of your design matrix refer to and what the corresponding beta parameters refer to. And then depending on what you want to do, so whether you want to see whether inclusion of a lot of regressors x2 or just a single regressor x2 is important for model comparison. That's up to what you're trying to do. So in terms of the splitting the simple linear regression model, which is the one that you're familiar with, of course the interpretation is that if you split it, and the only way you can split this is here, if you split it into just a column of ones, then this nested model just makes the prediction that the data is constant, and the joint model, so the full model, maybe better like this, so the full model makes the prediction that there is, in addition to the constant value, there is some covariation with the values of the independent variable. Yeah. But of course, the bigger, the more regressors you have, for example, multiple linear regression, then it depends on how you or what you want to look for. Yeah. And which kind of two models you want to compare. Good. So, yep.
So the full model and the reduced model are based on the same model? Or?
Yeah. So the full model is the mother model, if you want, and the reduced model is the first P1 columns of the design matrix of the full model.
So why do you compare them to each other?
Because that's what an F-test does. And the basic question behind that, as will also become clear hopefully, is whether the inclusion of these additional regressors, which are here in the X2, whether they make the explanation of the data better. So your main interest is in a way to check whether this set of regressors, X2, improves the explanation of the data, so increases the probability of your data under the model. Yeah? So you're essentially interested in this contribution. So this is already, having explained this, this is already where if one starts thinking about it, is a little bit, starts to wonder, so what is the difference between a model and a parameter? Because here, of course, the models that you're comparing are fairly similar. The main difference is that you restrict, for the reduced model, you restrict these beta parameters to be 0, because if they are 0, then of course the regressors in X2 don't make any contribution to the data. So this is a model comparison, but model comparison of very similar models.
Can we compare two reduced models, like two different?
Yes, you can also do that, but not with the F statistic. Yeah. So so the model comparison that we are looking here of comparing a full model to a reduced model is the model comparison in terms of likelihood ratio model comparison criteria that the F statistic does. Yeah. So you can do essentially you can compare any two models. You just need a model comparison criterion, and you need to evaluate that for your model. And so this is also, so likelihood ratio is not the only model comparison criterion, but it's a very common criterion, and for F tests it looks as we will see. Yeah?
So the F statistic can only compare one model to itself and not two different models?
Yeah. So the F statistics, if you see the F statistics as an implementation of a likelihood ratio, then you can only do what I'm telling you here. So I'm not telling you today about model comparison, all different forms that you can do. So another way to do model comparison is to compare the free energies, but that's so the variation in free energies as approximation to the log margin likelihood. But this is not what I'm telling you about today. Yeah. So there are many model comparison procedures, and I'm telling you about a specific one, namely likelihood ratio tests, likelihood ratio comparisons for the GLM, because this is what the F statistic does. Yeah. Anyone else who wants to compare different models from what we're doing? No. Good. So we are comparing these. So now we know which kind of models we want to compare, and now we have to think about, so we have given some meaning to our M1 and our M2, and now we have to think about these probabilities of the data under a given model. So these two probabilities or probability densities, as in our case. So we have talked about this before, so there's essentially not much new stuff in terms of these probabilities or probability densities, because we looked at maximum likelihood estimation before. And of course, this probability of data under a given model is what we used also in terms of our likelihood function. So if you remember let's start with the log likelihood function. So the log likelihood function, for example, for the beta parameter for the GLM was defined as the log of what? So we are in the GLM, and we discussed the log likelihood function for the GLM before, and then we used it for the beta parameter and also for the sigma square parameter. But how was the log likelihood function defined? It was defined as a log of something, but of what? It was in 2017. So. Yeah. although I would say under the parameters, because given always sounds a little bit Bayesian, and we are not in a Bayesian scenario, so we don't have a probability over beta. So it's oops, what have I done here? It's the probability of the data as a function of the parameter. So what this corresponds to is the log of y x beta sigma square in. Yeah. So we looked at these probabilities previously, and even more so, as I said here, these probabilities. So this is here a very general formulation, which is on the border of being wrong. So what we also looked is, of course, at maximizing this. So we are now interested in the probability that we get for our data once we optimized the parameter. Yeah? And we know the functional form of this ln PM1 and PM2 because this is the same thing as we dealt previously with in maximum likelihood estimation. Yeah. So likelihood and log likelihood is just the log and of the probability of the data under the model in the maximum likelihood framework as seen as a function of the parameter. Here, what we are interested in is actually once the parameter has been estimated, so that we just get a single value. So we are here interested in the maximum for our beta parameter. If we now look at a specific model of the log likelihood function, because the log likelihood function is just the probability of the data under the model. And we have also already computed its functional form. So do you remember that? When we maximize the log likelihood with respect to beta, so we are looking now at our reduced model currently. No, you should know that. So do you remember how the maximized log likelihood function looks like, assuming that we know sigma square? So we computed the log likelihood function once. Look back in your notes what we got there. No notes here or what? You found it? Come on. Yeah, it starts with that, yeah. So what was it?
Minus n over 2,
Mm-hmm.
ln 2
Mm-hmm.
minus n over 2, ln sigma square,
Mm-hmm.
minus 1 over 2 sigma square, times y minus x beta transpose times y minus x beta.
Mm-hmm. So this is actually this is what you just said, and this is actually this. So that's the log of the multivariate normal distribution over y with the expectation parameter x beta and the covariance parameter sigma square in. That's fine. And then we actually maximized it. So by maximization, we found our beta hat, maybe we need here a beta 1 because we're in this beta 1 scenario right now, sorry. We found our beta hat estimate, which is of course in this case this. And so this value of beta 1 maximizes the log likelihood function. So the maximum of the log likelihood function in terms of beta 1 is of course the value that we get for this function here if we plug in the maximum likelihood estimate. Yeah. So what we first wrote down was just the function as a function of beta, and now we are looking at the value of the function where beta is maximal. So if you want to visualize that, what we've just done is maybe we have this kind of function, and we first looked at it as a function f of x, and now we're looking at it as a single value at a location x hat, and the location x hat is exactly where the maximum is. Yeah, and then this is just a single number. Yeah, so it's just a scalar, a real number. Yeah. So that's this max L beta 1 that we now wrote down. And of course, the same thing for the same thing applies to our full model. So we now have our first probability or a log probability of the data under the model, and our second one I'm just writing up. So that's our standard model or full model. So what again are these things? So this is, we have a full model, which is this one, which we can of course also write as y x beta plus epsilon, because our x is this. And we have a reduced model, which is this. And now for these two models, we looked up these values, namely the probabilities of the data under these models, and wrote them down because we want to do a likelihood ratio comparison or a log likelihood ratio difference. To now get those whole thing even closer to the F statistic, it's helpful to define so-called residual sum of squares and residual errors. So if one defines E12 as y minus x beta hat, which is just the deviation of the data from the prediction of the full model, hence 1, 2. So this 1, 2 is for this x1, x2. And yeah, it's residual because it's once the parameters have been estimated, then one can re-express this last term here that is just above it as 2 sigma square E12 T E12, which is of course much more concise, so you don't always have to write y minus x beta hat transpose times y. And the same thing one can do here. So E1 we define as y minus x beta hat 1. So then we can express this term also as 1 over sigma square E1 T E1. Yeah. And now the last thing that we want to do is to actually evaluate the difference. Where are we? There. So we now want to evaluate this thing here. So if we now define a test, or not a test criterion, a model comparison criterion here, I call it delta, and might call it anything, and we define this as max beta max beta 1 R P1 L beta hat. No, sorry, not hat, because the max is implementing the hat. Then what we need to do is subtract this expression here from this expression here, and of course there are a number of terms which are all the same. So this is the same as this is the same as this, so we can get rid of that. And then we have a negative value. It's a little bit lost here. A negative value here for the residual sum of squares for the first one and for the second one. So now if we subtract this one, so if we subtract this, which is this part here, from this, then of course this negative thing gets positive. So we get to 1 over 2 sigma square epsilon 1 t epsilon 1 minus epsilon 1 2 t epsilon 1 2. So our log likelihood difference criterion for the two models that we're interested in comparing, namely the nested model and the full model, comes down to a difference of, if you want to call it, the residual sum of squares under the reduced model minus the residual sum of squares under the full model. Yeah. And now this difference, so this difference between the residual sum of squares of a reduced model and that of a full model, that is essential to the F statistic. So I haven't defined the F statistic yet. I will do after the break. But in the F statistic, we will see this difference as a fundamental quantity. And what I try to do here is to motivate looking at this difference from the perspective of model comparison by looking at likelihood ratios. Questions right now? Everything clear? Everything unclear? Nobody knows. Good. Then let's stop here and continue at 11 and then really look at the F statistic.